Work from Monday, page 819, questions 1 to 3. We're going to take a look at questions 2 and 3. Number 2 says uranium-235 nucleus absorbs a neutron and then splits into bromine and lanthanum and additional neutrons. We want to know how many neutrons are produced, and we want to balance the equation, express it as a balanced equation. Notice that in the example of nuclear fission that we have done, and we've seen it a couple of times actually, it's uranium-235 absorbing a neutron going to uranium-236, but it splits up into krypton and barium. In this case, it splits up into bromine and lanthanum. That's okay. There's different combinations that it can split up into, right? It is not just one fission reaction. Okay, this is one more example of a fission reaction. So we're going to start off with uranium-235. Has 92 protons. We know that because we can always check our periodic table if we don't remember it. It absorbs a neutron. Now, could I have put the neutron before the uranium-235? Sure, it doesn't matter, does it? We know it has to be on the left-hand side of the equation, but it doesn't matter which side of the uranium it's on. All right, it splits up into bromine, 87, plus lanthanum, 146. I could have change the order of these as well, put lanthanum first and bromine second. That wouldn't have mattered. Plus something, plus neutrons, additional neutrons. But how many additional neutrons? Well, let's figure that out. On the left-hand side, we have 236 and 92. On the right-hand side, we have to have 236 and 92 as well. But right now, if we look at this, we only have 233 and 92. So we're missing no protons and how many neutrons? 3 neutrons. Now, that's the same as the other example of nuclear fission that we've seen, where it's 3 neutrons. But understand that it's not necessarily going to be uranium splitting up. It could be something else. And it's not necessarily going to be 3 neutrons. It could be 2 neutrons or 4 neutrons. Look at each of them individually, even though the examples that we've done so far all have had 3 neutrons. All right, there's the equation. Now let's take a look at number 3 and find out how much energy is released in this. You guys know this, right? To find out the energy released, the energy ultimately comes from what? It's a 2-word answer. Yep, the mass defect. And to get the mass defect, which is the mass that disappears in this equation, okay, the missing mass in this equation, we have to get the mass of the left side and the right side. What's the mass of uranium-235? Yep. 0.043930. Okay, and that's going to be in atomic mass units, right? Okay, thank you. Now we're going to have to convert that to kilograms ultimately, but we're probably going to wait till close to the end to do that, so we don't have to do the conversion, 5, 6, 7 times. The mass of a neutron, 1.008665 atomic mass units. Now let's look at the bromine over here on the right-hand side. The bromine 87 has a mass of 86 711, thank you. And lanthanum 146 has a mass of 145 You notice the ones on the right-hand side are just under the mass number. The one on the left-hand side is just over the mass number. And then the neutrons, of course, we got 3 times 1.008665 atomic mass units. So let's get this side of the room, Cole's side of the room, to get the green side, the right side this time. And let's get Kelsey's side of the room to get the black side here, the left-hand side of the equation. If you've already got it, that's great. If you don't already have it, then calculate your side, please, to make sure that you can do that. Aiden, you have this number already in green? 8724. Thank you. Anybody else agree with that, guys? Okay. And the left-hand side in black, what do you guys get over here? Wilson, you got it? 052595. Is that right? Good. Odds are we're correct here. We can look at that and say, look, the left-hand side weighs more than the right-hand side, or the parent weighs more than the daughter, so we've probably done that correct. All right, now what's next? We got the mass of both sides. Brad kind of said it, right? The energy that's released comes from the mass defect, he said. So let's find the mass defect. Okay, the mass defect is going to be the difference in those two values. What's the difference in those two values? 0 point something, something, something atomic mass units? Yeah? 1.180098. Okay, thank you. Atomic mass units. Good. What are we going to do with that? In an ideal world, this question, we see it on a test, the mass is not given to us in atomic mass units. It's given to us in kilograms because it's less work if it's already in kilograms. But this is given to us in atomic mass units. So what do we got to do? Convert it to kilograms. We know that one atomic mass unit is 1.66 times 10 to the minus 27 kilograms, and that conversion factor is on the left-hand side of your data sheet. 0.180098 atomic mass units is equal to X kilograms. So let's get the value of the mass defect in kilograms. What's that going to be? 10 to the minus 27, 10 to the minus 28 kilograms? Something like that? Jack? 989626. With an 8 on the end? 9896268. Thank you. 10 times 10 to the minus 28 kilograms. Good. All right. What are we going to do with that? There's our mass defect, right? Hey, Brad told me a minute ago that the energy that's released comes from the mass defect. Einstein told us how to get the energy from the mass defect. We're just going to use his famous equation, E is equal to mc squared. So let's say it's 2.9896268 times 10 to the minus 28. You do want to use unrounded numbers here. Okay, we're talking not 3 or 4 decimal places, but as many decimal places as you have. We'll multiply that by the speed of light squared. And what do we get when we do that? Not the answer that's in our book here, but we'll deal with that in just a second. Who's got the answer that this works out to be here? Go ahead. 0.69. Okay, 2.69. Yep. And that's going to be in joules, right? We could leave it in joules, but if it's a multiple choice question on an exam, that might not be one of the options. They may ask us to convert it to electron volts or to mega electron volts as they have here. So let's do that conversion to mega electron volts. Let's first say 1 electron volt is 1.6 times 10 to the minus 19 joules equals X electron volts over 2.69066412 times 10 to the minus 11 joules. Let's get the electron volts. And then, once we get the electron volts, let's divide it by 10 to the 6, or multiply by 10 to the minus 6 in order to get the mega electron volts. So, what does it work out to be in electron volts? Going to be 167,800,000, roughly. Okay, if we divide that by 10 to the 6, we're going to get 167.8 mega electron volts. Right? Is that right? Oh, yeah. Yeah. Yeah, let's not go there, though, because that conversion factor is not on your data sheet.
Way that we did it, it's actually 168.166.
Oh, is it? Okay. We won't lose any sleep over that, though. Good. How many people got that? Okay. Some hands up there, but does it make sense for everybody? Something like this doesn't appear all that often, but it does appear, so we want to be ready for it just in case. Second bit of homework we had last night was page 775, which involved atomic transitions. Any issues with those questions on page 775? None? We're good with those? All right, let's take a look at one of them just to make sure that we're okay. Maybe number 2. How much energy does the electron in the hydrogen atom lose when it drops from n is equal to 5 to n is equal to 2 energy level? Well, if we go back to our table from 5 to 2. 5 is 0.55, negative 0.55, and negative 3.4. So what we're going to do in that case is say delta E is the final minus the initial. We're going from 5 to 2, so the final would be negative 3.4 electron volts. The initial would be negative 0.55 electron volts. The big deal with these is remembering to put the negative negative. Right? If you put negative 3.4 minus 0.55, you get the wrong answer. You get negative 3.95. But the reality is the answer is negative 2. What is it? 85, negative 2.85 electron volts. We're good there, guys? Okay, I want to take a look at one multiple choice question on this, and then we're going to move forward with our new stuff and finish things up. And the multiple choice question that I want to look at is on in your booklet. It's number 173. Don't bother submitting this one. Just do it real quickly, and then we'll do it as a class here when you're finished there, okay? All right, let's have a look at the question here. We see kind of an electron level diagram, kind of. It kind of reminds us of that, right, that we saw yesterday, the electron level diagram. But in the end, it's not an electron level diagram, because an electron level diagram shows us a little bit more detail. First of all, it's mercury, the one that we saw yesterday. The diagram that we saw yesterday was for hydrogen. That's no problem. We can see this for any element, including hydrogen, including mercury, sodium, or anything else. But a true diagram shows not only the energies, but it also shows the levels. And you remember that the levels are not equidistant apart. In fact, as we go up higher and higher and higher in the levels get closer and closer together. So it would look more like this if we were making it an electron level diagram. Does that make sense? All the way up to the infinite level, where the electron has actually become ionized, where the energy would be 0. Now, we said yesterday that these energy levels are negative values because we kind of think of it as us on the surface of the Earth. Okay, we're the electron that has left the Earth. Okay, we've dug ourselves out of the Earth. We're up above the Earth right now, and our potential energy is 0. As we dig a hole and go back down into the Earth towards the core of the Earth, then our potential energy becomes a bigger value, but a negative value. So as these electrons go back down towards the nucleus down here, they become a bigger value, but negative value. All right, we want to know the frequency of EMR that's required to excite mercury from W to Z. From W to Z. So you could say the first level to the fourth level, okay? If you want to think of it that way, it doesn't really matter. Okay, we're going to say, first of all, that the energy difference is equal to final minus initial. So it's going to be negative 1.6 electron volts minus negative 10.4 electron volts. Well, what do you get when you do that? 8.8 electron volts, and it's positive. Okay, that's not what we're looking for, though, right? This is the energy difference between those levels. We're looking for the frequency. What do you think you're going to do with this? How do you think you're going to find the frequency? Good. We're going to say that E is equal to H times F, and we're solving for frequency, so it's going to be E over H. It's going to be 8.8 electron volts over. What value of Planck's constant do you want to use here? 4.14. Now, listen, be careful. Okay, this is a question that you could see, absolutely could see. Okay, this is a good question, and in the grand scheme of things, a relatively straightforward question, right? Be prepared to see one of these diagrams solving for frequency of EMR given off or absorbed, or wavelength of EMR given off or absorbed. Not a crazy hard question, but pay attention to this. Okay, when you're doing one of these questions solving for F or lambda, do not use this energy or this energy. Use the difference. Does that make sense? The EMR that's released or absorbed doesn't come from the energy of a level, ever. The EMR absorbed or given off comes from the energy of the transition. So it's always got to be the difference. Okay? We never use the energy of one level for anything in Physics 30. Okay, if we're going to do something with this, it's always, whether it's frequency, energy, wavelength, whatever we're trying to do, it's always going to be the difference between the two levels. Got it? All right. It seems to me there might be something like that appearing on your practice, on your little mini assignment as well. I can't remember for sure, but I think there is. All right. I want to go over one quick little model of the atom. This is going to be our last model of the atom, and this is going to take us about 4 to 5 minutes. We'll take a little break, and then we're going to finish up things in Physics 30 for the last half-hour class here today. So we got the Dalton solid sphere model of the atom. Sometimes I like to call it the marble model, right? Because it's like the atom consists of solid sphere, like a marble consists of a solid sphere. They're different, but there's nothing inside them. Marble's as small as it gets. The atom is as small as it gets. And then we went to the Thompson model of the atom, the Thompson model of the atom, the plum pudding model of the atom, the chocolate chip cookie dough model of the atom. The electrons are floating around in a sea of positive charge. Big deal, because we acknowledge the existence of subatomic particles. But subatomic particles, the placement of them, the function of them inside the atom, all wrong. Okay, but at least they're subatomic particles. Then we went to Rutherford, which was the planetary model of the atom. Big step forward, because the structure of that atom looks a lot like our current notion of the atom. Okay, you got a small, dense, positively charged nucleus. You got electrons orbiting around it. Then we went to the Bohr model of the atom, which said, basically everything Rutherford said is correct, but these electrons have to be in very specific spots. Okay, they're characterized by certain energies, so they're on certain levels, characterized by certain energies. They're in stationary states, right? They should be giving off EMR because they experience a centripetal acceleration, but they don't emit EMR, so it's like they're stationary. And finally, they can make transitions from high levels to low levels and vice versa. Finally, we have the Schrodinger model of the atom. Sometimes we call the Schrodinger model of the atom the quantum mechanical model of the atom, or sometimes we call it the electron-cloud model of the atom. Just like the Thompson model of the atom, sometimes we call it the plum pudding model of the atom, sometimes the chocolate chip cookie dough model of the atom, the Dalton solid sphere, the Dalton marble model, okay, the Dalton pool ball model. Lots of names for these things, right? Here's the guys' names, though: Dalton, Thompson, Rutherford, Bohr, Schrodinger. Quantum mechanical model, electron-cloud model. What I want you to know with this, guys, is the following. It's, in a sense, a step forward, and in a sense, a step backward, all at the same time. It is about 85 years old, this model of the atom, and it is still the model of the atom that we accept. So there was between 1897 and 1930-ish, there was a lot of stuff going on in the development of the model of the atom, right? We went from Thompson to Rutherford to Bohr, and then around 1930, we went to the quantum mechanical or electron-cloud model of the atom, and we're still there. So we think we're right now, because we've had this around for about 85 years. We think we're right. But as I said, it's in some ways a step forward because it improves our understanding, but in some ways a step backwards because it acknowledges uncertainty. We're not sure about certain things. The step forward is that, although the step backward is that we're not sure about certain things, but the step forward is that we know that we can't be sure about certain things. So we understand that we can't know certain things. Does that make sense? So in a sense, that's a step backwards, right? Because we can't know it. But we know now, at least, that we can't know certain things. So basically, what does this model of the atom say? Well, it says there's a small, dense, positively charged nucleus with protons and neutrons, and it says that there's electrons orbiting around this nucleus, just like the Rutherford model, just like the Bohr model of the atom. But we've learned a little bit, especially one day we were talking about last unit, the de Broglie hypothesis, the idea that electrons and other particles can have a wave nature. We're going to say here, guys, that these electrons, as they orbit around, are orbiting around the nucleus as waves. So they don't necessarily have an exact location. It's not like we're going to pinpoint a location of these electrons, right? Rutherford said they can orbit around wherever they want. Bohr said it's here. It's right here. The quantum mechanical model says, yeah, hold on a second. You can't say it's right here because it doesn't really have a particular spot per se, because it's orbiting around in a wave. It's kind of orbiting around somewhere within a cloud, hence the electron-cloud model of the atom. Now, there's a certain probability that when we go to look for it, we're going to find it here. There's another probability when we go to look for it that we're going to find it here and here. And there's a certain probability that we're going to find it way the heck out there. Okay, but it is based on, just like radioactivity as a quantum process, it's based entirely on probability, on statistics. We don't know where it is. In fact, we can't even say that it has a specific spot. We can make a prediction based on probability where we're going to find it. Now, the most probable location for it, the most likely location, is exactly where Bohr thought it was going to be. We're not saying that electrons aren't existing on levels still. They still exist on levels. It's just that the location is not necessarily exactly where Bohr said that it was going to be. But that's the most probable location. It's kind of like this. Kind of like this, guys. Okay, if Cassidy is misbehaving, and I send her to Mrs. Stafachuk's office, and Cassidy, go to the office right now. Go to Mrs. Stafachuk's office, and Cassidy says, where would I find Mrs. Stafachuk? Well, in her office. Right? Well, are we for sure going to find her in her office? That's the most probable location for Mrs. Stafachuk, right? In her office. But we don't know for sure that she's there. That's, if we had to make bets on it, that's where we're gonna bet that she's going to be. But she could be down the hallway in the math wing. She could be down in the science wing. She could actually be at our board office having a meeting. She could actually be in Calgary somewhere picking up something for grad commencement. She could actually be in Costa Red Deer where her mom lives. Okay, maybe she went to visit her mom. Maybe she's even, you know what, maybe she even got on a plane this morning and went to Mexico. I don't know, I haven't seen her. Okay. The further away she gets from the most probable location, from her office, the less the probability gets. But there still is a real probability that we're going to find her there. There is a real probability that she's in Mexico right now. I just think it's a really, really, really small probability, that's all. But it's still real. Right? There is a real probability that these electrons can be anywhere. It's just a smaller probability as we get further away from the Bohr radius. Does that make sense? So what do you got to remember about the electron-cloud model of the atom? Basically, associate Schrodinger, quantum mechanical, and electron, those three words, those three terms together. Associate them together. Okay. The word probability is big. Okay. The word wave is big. The electrons are orbiting as waves. And just understand that, look, you don't have to understand every detail of the quantum mechanical model, not at all. But understand that, you know what, we don't know exactly where we're going to find it. We're just going to predict where we're going to find it. That's all.